Okay, so first I'll say a few words about the final. We will use the university scheduled time for the final exam, which will be next Monday from 3 p.m. to 6 p.m. So we will use the full 3 hours. But I think based on my estimation, the exam problem should take 2 hours, like if you are very familiar with the material, but we still want to give you the 3 hours to make sure everybody has enough time. So we will not run into the midterm issue, like some of you may know the material, know the answers, but have limited time. So that's the plan. And as the syllabus said, we'll go with the syllabus. You are allowed to bring one piece of paper, like the letter size paper, double-sided. You can write anything you think is important on the note and bring it to the exam. So, and we will provide you with scratch papers, enough white papers for you to use. But after the exam concludes, we will ask you to turn in both the notes and also the exam paper and the scratch paper. So regarding the coverage, so I would like to say roughly, not accurately, but roughly, I would say maybe 2/3 of the problems will be from after midterm. So the ones we didn't cover in the midterm, that will be the focus of the final. So 2/3 of the problems will be after midterm, but 1/3 will still be from the pre-midterm materials. So in other words, if you want to do really well, you still need to review the pre-midterm materials a little bit more. Yeah. So, but I would like to say that you're allowed to bring a scientific calculator, that's allowed. But I can say that calculation is not really an emphasis for the final. So you're still going to use the mathematical notations to do most of the calculation operation instead of using numbers. I hope that clarifies. Okay. So, and also I have moved my office hour to Friday. So therefore, you're going to have the TA's office hour tomorrow morning and my office hour Friday morning. So you can have time to ask your questions for preparation. No, it's no longer multiple choice. It's more like your homework problems. So you're going to write solutions to a problem. You are going to try to write the steps. Yeah. And also, if you have any health concerns, please let me know as soon as possible, and we will try to help everyone out to make that not a burden for the final exam. Okay. All right. So
how many I'm sorry, I just have a question. How many questions do you think the final is going to be, like, or if not, like a range of questions you think it'll be if you haven't decided that yet?
Sorry, how many questions?
Yeah, this is how many questions do you think it will be, and if you haven't decided that yet, like a range of how many questions do you think it would be?
I don't think that matters. The reason is that the time it takes for a true/false question is definitely different from the time it takes for a long question. But I would say, roughly speaking, for the number of questions similar to your homework question, probably I think the amount of work is similar to one homework. About that. Yeah, about in terms of amount of problem, that's similar to one homework. Yeah, but we will try to ask some true/false questions, which will be quicker to answer. Yeah, and some may require some detailed answers. Yeah.
Okay, thank you so much.
Yeah.
Hi, Professor. Are we gonna have a practice final exam before the actual final?
I wouldn't say so, because we don't have so many problems. That's the honest answer. But I would say the textbook, I recommend it. If you have an electronic copy of that, there are a lot of practice problems in the book. And also, I would say the style is very similar. And also for the review I'm going to do on Wednesday, I will try to do some problems with you. So that can be also considered as a practice.
Okay, thank you.
Yeah, but the style is very similar to your homework. That's the thing I can say. So if you did your homework independently, then I don't think you should have much trouble with the final. But the difference is that you have a limited amount of time for the final, 3 hours. That's the major difference. Okay, so I would say the best way to review is to make sure you can solve all the homework problems in a quick way, right? If you review them, you did them before, you can see whether I still remember how to do it. That's the one part for the review. And also for the midterm, if you still have some questions unanswered, please ask them before the final to make sure you really understand why the solutions are like those. And also for the lecture notes, I think the best way is to really go over lecture notes to make sure that you understand every step. And if you do not, please ask. So that would be my advice. Okay. So let's continue. So today we are going to wrap up about our discussion on the hypothesis testing. So let me pull up my screen. Okay, so last time we talked about hypothesis testing, which you learned from an introductory class before, but here we want to give you more insights about the concept and the mathematics behind it. So as a review, for a test, there are 4 elements. The first 2 are about the problem formulation. What's the null hypothesis? What's the alternative hypothesis? And they are both about a parameter. So usually the null hypothesis is about the equation about parameter, whether the parameter equals a value you specified. And the alternative hypothesis is often an inequality if it's one-sided, or an unequality, which if it's two-sided. So you are going to make a choice between those 2. That's what you're going to do. And your default is the null, which means that you have a strong preference for the null until your data tells you a strong evidence that you might reject the null. So that's the whole philosophy. And to do that, you need to summarize your data using a test statistic. So often the test statistic is constructed from an estimator of the parameter. So here the parameter is denoted by theta, and the estimator is by theta hat. So we are going to construct the estimator from theta hat because you know you can calculate theta hat from data, right? The theta hat is a formula. You apply it to your data, then you get a number. So we call that as the realization of theta hat. But how can you go from there? So your decision will be based on the distribution of the random variable theta hat under the null hypothesis and the realization, the number you observed for theta hat on your data. So comparing the realization to the null distribution, you are going to make a decision. So the construction of the test statistic is trying to transform theta hat in a way such that the transformed test statistic can follow a nice distribution under the null. And hopefully the null distribution doesn't involve any unknown parameters. That's our goal. Okay, so the 4th component required is the significance level, which will decide your decision threshold when you make a decision about rejecting the null versus not rejecting the null. Okay, and we said that there is some correspondence between the test and the confidence interval. So if your significance level is alpha and your test decision is to reject the null, that theta equals to theta 0, this specified value. This is equivalent to say that when you construct a 1 minus alpha confidence interval of theta, this interval doesn't cover the specified value theta 0. So there's a 1-to-1 correspondence between these 2 approaches. We talk about confidence interval first. Now we are talking about the testing approach. So then we talk about the specific example about testing the mean of this normal distribution, whether this mean is equal to mu0. And we have a sample, IID sample of n random variables from this normal distribution. Here, naturally, the estimator is the sample mean called xn bar, and we denote it by mu hat. And we actually know that under the null hypothesis, xn bar or mu hat follow this normal distribution, right? Because we're under the null, so the mean is the mean mu0, and the variance is sigma squared over m. So we first use the simple approach to assume, oh, let's say sigma squared is known. So then we want to find the null distribution of a test statistic, and hopefully the null distribution doesn't involve unknown parameters, or it's a nice simple distribution. So our strategy is just to do the standardization of the mu hat or xn bar by subtracting the null mean, dividing by the standard deviation, which is sigma over root n. So this is called a z statistic, actually. This z statistic, let me put it here. So this has a name called z statistic. But to me, I think the name is not the most important thing. The most important thing is to understand the derivation. This follows a standard normal distribution, which is a nice null distribution. Okay. And if sigma is unknown, we need to use its estimator. So the natural estimator for sigma square, the population variance, is the so-called sample variance. We do division over n-1 to achieve unbiasedness. And this is known to follow what? A chi-square distribution with n-1 degrees of freedom, right? So therefore, by constructing this ratio, we could have this so-called T statistic follows a T distribution with n-1 degrees of freedom. And this distribution also doesn't involve any unknown parameters. So let's use the T statistic to continue from here. So given that we know it's null distribution, how do we make a decision based on its realization on the real data? Let's call it T star. So how can we make a decision based on the null distribution of the capitalized T, T star, and the alpha significance level? There are two approaches. One is to use the p-value approach. And this approach is going to first convert the distribution of capital T under null and the realization T star into a tail probability called p-value. So the definition of p-value, whether as the left tail, right tail, or two tails, depend on the alternative hypothesis, depends on what we call more extreme. So if the alternative is two-sided, then we will consider the two tails both mean two extreme. So then the sum of the two tails, or by symmetry, because here we have the T n-1 distribution as the null distribution, which is a symmetric distribution around 0. So these two tails are actually equal. So taking either one, we multiply by 2. That gave us the two-sided p-value. Or if we are interested in the one-sided p-value, it will be just the right tail or the left tail. So that's how we combine these two sets of information, the null distribution, the realization of the test statistic, into a p-value. Then the decision is simple. We are going to compare the p-value against the significance level and say whether we want to reject the null. Okay, so that's one approach. The other approach is that we don't have the concept p-value. Instead, we just directly define the rejection region based on the significance level and the null distribution. So let's say we want to have a significance level alpha. Then for a two-sided test, we're going to put alpha over 2 here, alpha over 2 here, and find those two corresponding values. Then the rejection region will be the left tail here and the right tail here. So as long as the test statistic falls in each side, we call the union of the two sets as the rejection region. As long as the T statistic follows into the rejection region, or I mean the T star, the realization falls into the rejection region, we reject the null. So this is a more straightforward approach. So I would say in most intro classes, maybe you learn this first. But the p-value approach is more common in practice. And the reason is that this p-value doesn't change with alpha, right? You can set your alpha afterwards to say whether I want to reject the null or not. But the second approach, alpha must be preset and specified. So the rejection region is defined. Okay, does that make sense? Okay. So this is what we said last time, a review. So following that, there are a few concepts associated with the test. Okay, so one is what we call type 1 error. So type 1 error, okay, is what we defined as the probability that our test rejects the null hypothesis under the null hypothesis. So it's basically a probability computed under the null, okay? And here the randomness is the test, it's the test statistic. So basically I can write this as the T falls into the rejection region, because when the T falls into the rejection region is when we reject the null, right? And we compute this probability for T, for capital T following a distribution under the null. That's what we mean. So therefore, you can see that based on the rejection region we defined in this way, if we can define the rejection region based on alpha so that these two tails together have probability equal to alpha, then naturally this is equal to alpha, right? That's how we define the rejection region. So I'm saying that in the ideal case, the rejection region is defined to have probability equal to alpha under the null. Then this probability should be equal to alpha. This is the most ideal case. So in other words, alpha is what we call the significance level, which is a parameter of our test. But I can say for this class, it is okay that you just understand that type 1 error equals alpha. But I want to tell you that in practice or in more advanced cases, advanced tests, this may become less or equal than. So the reason is that in some cases, you may not be able to find. So for example, the null distribution of the test statistics is super complicated. It's not simply a standard normal or a T distribution. So you can have a very exact solution for finding the rejection region. So if you don't have such a nice distribution and the rejection region is only to satisfy that the probability of in the rejection region is less or equal than alpha, if that's the case, then your type 1 error is less or equal than alpha instead of equal to alpha. So that could happen. So in other words, you are being conservative because you cannot be exact. So I'm just making this note here. But for this undergraduate level classes, the test we introduced allows us to find the exact rejection region. So we can say this is equal. Okay. And the type 2 error is defined in another way, and I'll explain why they're errors. It's defined as the probability under the alternative that the test does not reject null. So you can see these two are both errors because under the null hypothesis, which means that we assume the null is true, we want to keep the null, right? We don't want to reject the null. Then in this case, when you reject the null, you make an error. So that's why we call this an error and we give it type 1 label. This is the other way around. We're under the alternative. The alternative is true. So we want to reject the null, right? So we go for the alternative. However, if the test makes a mistake by not rejecting the null, then this is an error and we call this type 2 error. So you can see they are just like the trade-off, right? Type 1 error, type 2 error. All right, so then this is equivalent to say that it is the probability that the test statistic falls out of the rejection region. Okay. So how do we define this? And we give this a notation, actually. We often give this a notation and we call it beta, just as opposed to alpha. Okay, and so related to that, we have this relationship for another quantity, which we define as power. It is defined as 1 minus beta. So in other words, type 2 error plus power equals to 1. So therefore, you can also say that power is basically the probability under the alternative that the test rejects the null, which is nice. And also it's equivalent to the probability under alternative that the test statistic falls into the rejection region. Okay, so to realize this calculation, so what we will do, probably let's go to this case. Go to this case. So you can see that here we cannot really compute the type 2 error given this alternative. The reason is because here we don't tell you what the alternative value for mu is. We just say it's not equal to mu0. So in another case, under the alternative, the mu value is unspecified. So therefore, we don't know exactly what the distribution of t is under this alternative. So that's why we cannot really do this calculation for this composite, the composite alternative. So we don't have a specific value. So what I want to say is that these two things, okay, can be computed when we are under the simple test scenario. They are computable when alternative hypothesis, I should write H1, is simple. By simple, I mean, so like the alternative hypothesis says mu equals to mu1. And of course, the mu1 must be different from mu0. So this is the case where the null hypothesis says, oh, mu is equal to mu0. Alternative says mu equals to mu1. So you are going to choose between those two mu values. And in this case, you could compute the mu1. You could compute the test statistic distribution under the alternative. So I'm going to give you an example for doing this, right? So let's say when you're under the alternative, mu equals to mu1. And for this test statistic, what can you say? So let's do the comparison. So under the null hypothesis, still back to this example, this normal sample example, we have said xn bar minus mu0 over Sn over root n. Okay, this follows a t distribution with n-1 degrees of freedom. This is what we derived last time or based on the previous lectures. Now, under the alternative, the true mu is no longer mu0, but mu1. So therefore, our theory told us it should be xn bar minus mu1 over Sn. This should follow t distribution with n-1 degrees of freedom. Does this make sense? So this reflects how the different hypotheses tell us different distributions of our xn bar. Okay. So therefore, you can see there is a relationship between those two. If we call this as our test statistic t, then what is this? This is actually equal to t plus mu0 minus mu1 over Sn over root n, right? So we need to do adjustment to our t to make this one, because this is no longer t. So Therefore, if our rejection region is based on our T, the null distribution of T, we need to derive a distribution of T under the alternative to calculate our power and type 2 error. This is the task we are dealing with right now. Do we have questions so far about what we have said? Okay, no, great. So now let's say that in this simple test, let's look at our rejection region. So let's just assume, and there is a short term called without loss of generality. This is a short term in mathematics, which means that we are assuming a condition, but this condition is not special. If we assume it in the other way, the same argument follows. So this is just a way to simplify argument. We can assume that mu1 is greater than mu0. So the specified value under the alternative is larger than the specified value under the null. So if we specify the other way, less than, the same argument carries. So that's why we can say this is without loss of generality. And so under this assumption, then we can have the rejection region, right? So the rejection region should take the form T greater than some constant A. The reason is that here the alternative mean is larger than the null mean. So we want to reject when the test statistic is large positive. So the right tail will be our rejection region. So therefore, let's say given the significance level, alpha, okay, and then let's draw the distribution of this T distribution. So this is the Tm-1 distribution, okay? And let's say that we have the right tail as our rejection region. Then we are going to reject the interval larger than A so that the probability of log T of this test statistic larger than A is equal to alpha. So basically, we are going to find A such that the probability under the null that the test statistic T, we just wrote last page, larger than A is equal to alpha. So basically, this A is the 1 minus alpha quantile of that T distribution with n-1 degrees of freedom, because that's the distribution of this capital T under the null. Okay, so we have the rejection region and we have the test. So the test means that, so the test we establish is this. Let me just rewrite this formula again. We use the sample mean x and bar minus mu0 specified under the null divided by the standard deviation of the data divided by root m. This is our T statistic, and we are going to get its realization. So calculate its realization, which we call T star. Okay, so this realization is by applying this formula to our real data. Let me just denote them by small lower cases. So I call small x and bar minus mu0 small x m over root m. So I have this number. Then my decision is to compare this T star with the rejection region. So from there, I would say if T star is larger, maybe I should put this equal then. I think I can add an equal, larger or equal than A. Our decision is reject H0, reject the null. Otherwise, which means that T alpha is less than A, we do not reject the null. So therefore, this is the test, and this is how we make a decision. And type 1 error in this case is equal to alpha. And the type 2 error needs our calculation, denoted by beta. Is basically the probability under the alternative, not the null, but the alternative that T is less than A, which means that we don't reject. Okay. So how can we compute this distribution? Now we need some change. So the reason is that here under the alternative, T, this definition no longer follows a null distribution, no longer follows a T distribution with n-1 degrees of freedom. But we need to use the other form. So we can write this T out, right? So this is basically xn bar minus mu 0. Okay, so what I want to say is that this doesn't follow Tn-1 under the alternative. But we want to find the form that follows this Tn-1 under alternative so we can calculate the probability. And from the previous page, we know we just need to replace this mu 0 by mu 1. So let's do it. So let's just create the form we want. The left-hand side is equal to xn bar minus mu 1 over Sn over root m. Okay, and let me see, plus mu 1 minus mu 0 Sn over root m. So you can see that this sum is just equal to this, and I didn't do anything else. So I just re-expressed this as this. And now for this one, because now we're under the alternative, we know this follows Tn-1 under the alternative. So this allows us to calculate the probability. But we still have one obstacle in the middle. That's about this term, right? So you want to move this term to the right-hand side, then use the distribution of this term. This is the random variable we work with to derive a probability. However, this term itself is not a constant. Okay, we must bear in mind that because Sn is random. It's our sample variance square root. So how do we do that? So we are basically pretending, if we do that, so let me just say, okay, if we move it to the left-hand side and say, this is the random variable we work with, and we want to compute its probability under A minus okay, so if we do that, and then we are going to say that using the T distribution with n-1 degrees of freedom. So still, let me draw the figure. This is the T n-1 density, and this is 0. And now let's say that we have, originally we have A right here, right? So now we are going to move A, this is A. We are going to move A to this part, and this is what we call A minus mu 1 minus mu 0 over Sn over root m. So then the type 2 error is what? The type 2 error is actually this part. This is the probability we're going to compute. Okay, so that's it. So if we're going to do that, then we are going to say this is equal to this area. So basically, it's about the probability that a T random variable following this Tn-1 distribution is under this threshold. Okay, so let's say if I give this a CDF, called F, then this is basically this. Okay, where F is the CDF of T n minus 1 distribution. So we could do this, but what I want to say is that this step is itself an approximation. So from here to here, this step we make an important assumption. So we are treating SM is treated as fixed. Okay, so you see, our result involved this Sn, and this Sn is not really considered as a random variable. Otherwise, this is not valid. We are basically putting in its observed value, its realization on the real data, from the real data, put that value in, and pretend that it is the true standard deviation, sigma. So that can make the logic follow. Okay, so this is a type 2 error. And then the right-hand side, 1 minus theta is the power. So therefore, you can see one thing, right, from this term, this threshold. This threshold tells us an important message. The left it is. If we shift it to the left, the smaller the beta, the larger the power. Because power is a good thing. Under the alternative, we want to reject the alternative, right? We reject the null. So the power 1 minus beta is basically under the alternative t larger or equal than a. So this is our power. So this is our power. So if you look at the power, you can see that it increases as we shift this threshold to the left. And shifting the threshold to the left is equivalent to say that this mu1 minus mu0 is large, right? Since we're going to minus this positive part, mu1 is larger than mu0, their difference is positive. But if I enlarge their difference, it means that I'm going to shift the threshold to the left. So I'm increasing the power. So what this suggests is that the larger mu1 minus mu0 is, the greater the power, which makes sense because the larger this difference is, the more different the null and the alternative hypotheses are. So that means we can better distinguish alternative from the null, right? That implies better power. So everything is connected intuitively. Okay, so I hope I give you this example about power calculation. So you are going to use the distribution under the null, under the alternative separately for the power calculation. So the key is that you can no longer assume the t follows a Tn-1 distribution under the alternative because the mu parameter is different. So you're going to construct a new statistic that follows the t distribution under the alternative. And you can construct that based on the t statistic. Does that make sense? Okay, so if you have any questions, please feel free to ask anytime. So that's for the mean calculation. For the mean test, right? We test the mean equals to mu0 or not. And when the sigma variance is known, we use the z-test. When it's unknown, we use the t-test. But in practice, you can know we almost certainly don't know the variance. So it must come from the data. So the t-test is the common practice. Okay, and also I want to say that example we gave you is based on this assumption, this normal assumption. So I think I should grab the previous page, yes, about this normal assumption. But I want to say that this result can approximately hold even though the sample is not from a normal distribution, because you have the central limit theorem to help you, right? So when you don't have this normal assumption that your n is very large, you could use the central limit theorem by saying this is still approximately standard normal. So you could still do that. And also, just as a quick reminder, although not an emphasis of this class, but the reminder is that there is a condition for central limit theorem, that is the distribution of x1 to xn must have finite variance. The finite variance is a condition that needs for the central limit theorem to hold. And later, if you take more advanced classes, you may know there's a Cauchy distribution which doesn't have finite variance or finite second moment. So, but that's more advanced topic. But here in this class, you can surely assume that the central limit theorem holds because we give you the nice distributions to work with, like the exponential, Poisson, Bernoulli. These are all the nice distributions for which the central limit theorem can hold. Okay, so these are about testing the mean. Let's do one more example about testing the proportion. So now let's say that we are under this case, x1 to xn, IID from a Bernoulli distribution with parameter p, success probability parameter p. So what this implies is that expectation of each xi is just equal to p. And also this is just the probability that xi equals to 1. They're the same. Okay, so here our test is about the null hypothesis that p is equal to a specified value p0. In most cases, we are interested in p0 equals 0.5 because that is suggesting whether the coin is fair, right? If you're doing a coin flipping, a fair coin should have p0, should have p equal to 1/2. So that's why a common value for p0 will be 1/2. So the alternative could be equal to p unequal to p0, that's two-sided, or larger than or smaller than, depending on the question you are going to ask. So do you want to say, the coin is giving me a less than 1/2 chance, so then I'm losing, right? Then you want to choose 1/2, less than. Or if you think you're gaining an advantage, you may choose greater than. Or if you don't care which direction, just fair or not, you go for unequal. So for this one, we are going to construct our test statistic, right? Remember, we have the null hypothesis, alternative hypothesis, the test statistic. The test statistic, naturally, we need the estimator of p. So the estimator we call p hat is naturally just the xn bar, the average. But we wanted to have a nice distribution under the null, right? So under the null, p equals p0. What we could easily do is to just standardize this p hat based on the null mean, and then we can use the central limit theorem. So by the central limit theorem, we have approximately p hat follows approximately normal distribution with mean p0, right? The true mean is now p0, and the variance is p0 times 1 minus p0 over m. The reason is that for each xi, its variance is just p times 1 minus p. Okay, so we want to have a nice distribution under the null, which is a simple, easily looked up distribution. In the old days, we need to look up a normal table. So that's why we want to make sure the normal distribution is the standard normal, so we can use the table. So therefore, the test statistic can be simply constructed as p hat minus P0 over standard deviation. Okay, and I want to clarify that here I use the capitalized T just to mean the test statistic. I didn't specify to be the T statistic. The reason is that here we are actually not, this is not a T statistic because everything comes from the null hypothesis. So we can call this a Z statistic, I think more exactly. But here I'm just using the notation capital T to refer to the test statistic, the random variable in general, to be consistent. And I don't think the name is as important as the understanding. So that's why I use the same notation. So now this one, by the central limit theorem, would follow approximately standard normal. So we are happy, right? So then the conversion of this T statistic and its realization to a p-value or doing the rejection region would be natural. So let's just say that we do the p-value approach. Okay, so it will be under, so given we call this realization of the capitalized T as T star on our data, then the p-value is defined as the probability under the null hypothesis that is capitalized T has absolute values greater or equal than the absolute value of the observation of the realization. So I'm saying here we are doing the two-sided alternative. Okay, so here this p-value is under the two-sided alternative. P doesn't equal to p0. Okay, and then you're going to just use the two tails from the standard normal. So I'm just going to plot it. Right, so if you have the absolute value of T star right here, and its negativity right here, then the p-value would just be both tails. You add them up. Okay, so that will be the p-value. And then you compare it to alpha. If it's less or equal than alpha, then you reject the null. So if p-value is less or equal than alpha, you reject the null. Otherwise, do not reject the null. Okay. Does that make sense to everyone? Okay, and we have a question. What sample size is considered large in this case? I saw sample size 10. Yeah, if it's just one parameter, I would say a sample size of 10 is good enough. So basically, if you look at the standard deviation of the average, right? So the standard deviation is in the order of root m. So basically, you can roughly think how that will give you some idea about how large the m plays in. But I think that's a quite vague way of describing. I would say for the central limit theorem, in practice, people usually think they can safely apply it when the sample size over the number of parameters is 20, is at least 20. So like here, if you have one parameter to estimate, you have 20, sample size 20, you can use it. But in the homework, actually, we allow you to use central limit theorem, so the 10 is also considered okay, because you know the homework is a practice, right? And sometimes we try to simplify the calculation for you. But in the final, if you are unsure whether central limit theorem is applicable, I think I'll try to make the problem clear and self-explanatory. But if you have questions, you can just raise your hand. Okay, so that's all I want to say for this one parameter testing. And also, of course, we can compare two conditions, right? Comparing two conditions is more common in practice. And we have seen the confidence interval for two parameters and their difference. We can also do that for the testing. So using the testing framework, we can also answer the two sample comparison problem. So let's say that we have x1 to xm from one normal distribution with mean mu1 or mu x. Let me be consistent. Mu x variance sigma x squared. You remember we saw this setting before. And we have y1 to ym. They are under IID. IID from a normal distribution with mean mu y and variance sigma y squared. And these two samples are themselves independent. Okay, and they are independent. Are independent. Okay, so the null hypothesis most commonly studied, you will see, is you are interested in whether mu x equals mu y. Okay, and the alternative is often mu x doesn't equal to mu y, unless you have a special preference to see which one is bigger. So for example, you may wonder, for example, like the x1 to xm is the measurements, some quality score measurements before technology improvement. And y1 to ym are measurements after the improvement. You want to know whether there's any actual improvement, then in this case, you may go for less than. Okay. So therefore, you can see that the alternative hypothesis depends on the question you want to ask from the data. So for this, you can actually consider this null hypothesis in our old way, which is it's a parameter value equal to something. By simply reorganize the terms, I can write as mu x minus mu y equals 0. Right? So 0 is my specified value, and the parameter of my interest is now mu x minus mu y. So that's our null hypothesis and alternative hypothesis. The next question is the test statistic. So using our familiar logic, we want to start with the estimator of the parameter, right? So the estimator would be mu x hat minus mu y hat, right? The difference of the two estimators. And naturally, because we are working with the means, we would use the sample mean as an estimator for the population mean. So therefore, I will say it's xm bar minus ym bar, because for y, the sample size is m. And then, do we know their distribution under the null hypothesis for this one? Yes, we do. We know the distribution of xm bar, which is normal, the distribution of ym bar, which is normal. And because of the independence of the two samples, their difference is also normal. So therefore, under the null hypothesis, or I should say, maybe let's just talk about a general form first. So this should follow a normal distribution with mean as mu x minus mu y, variance as sigma x squared over m plus sigma y squared over m. Okay, that's what we have. And then what else? We need to specify this distribution under the null. Okay, so under the null, we are told mu x minus mu y equals 0. So therefore, would follow normal distribution mean 0, variance okay. And we want to standardize this so the null distribution has a nice clean form, the standard form. We can look up table, right, in our textbook in the old days. So therefore, we define our test statistic T just as okay, and this would follow. All right. That's the null distribution. But of course, this is by assuming sigma x squared and sigma y squared are known. Okay, then we're done. So this is the test statistic. And then given its realization, depending on the alternative, you are going to convert the test statistic null distribution and also the observed value into a p-value. So say the realization is t star, okay? Then the p-value is going to, let me just write down all three cases for your information, is the probability that this t under the null is larger than the t star in terms of absolute value if the alternative is mu x doesn't equal to mu y. Okay, but if the alternative is mu x greater than mu y, which means that their difference is positive, then I'm interested in just the right tail. Maybe let me put this larger than t larger or equal than the t star, that's the right tail. In the last case, if the alternative is mu x is smaller than mu y, which means mu x minus mu y less than 0, that's our alternative. Then the p-value is the probability that t is less or equal than t star. So we talk about the p-value in all three cases. Okay, here we are assuming that sigma x squared and sigma y squared are unknown. But what if they are unknown? But what if they're unknown? So here in this case, let me talk about which we call the two-sample t-test. So which is the most commonly used test in practice? T-test, two-sample t-test. Okay, so in the two-sample t-test, we added this assumption. We added that sigma x squared equals sigma y squared. Okay, this is the additional assumption besides the two normal distribution assumptions. So these two are still needed, but besides, we need this equality. The reason is that we are going to provide a test, or we're going to provide what we call an estimator for this pooled variance. So since they're equal, we just denote them by sigma squared, okay, by a common term sigma squared. And how do we estimate this sigma squared? So we provide this called pooled sample variance. Okay, so this is defined as n minus 1 times the sample variance of the x sample as x squared plus n minus 1 times the sample variance of the y sample divided by n plus n minus 2. Or the denominator can be just interpreted as n minus 1 plus n minus 1. So if I expand it, then you can see what is that. So it's basically summation I from 1 to n xi minus xn bar square, okay, plus another summation I from 1 to m yi minus ym bar square. Okay, so I take the sum for each sample divided by n plus n minus 2. Okay, and this makes it easy because we know the distribution of this pool sample variance. So we just do this calculation together. So recall that a very important theoretical result we did before is n minus 1 times sx squared over sigma square follows what? Follows chi-square distribution with n-1 degrees of freedom, right? We learned this before. And similarly, n-1 sy square over sigma square follows chi-square with m-1 degrees of freedom. Okay, and they are independent because x1 to xn and y1 to ym are independent. So we have sx squared independent of sy squared. So this perpendicular sign is often used to denote independence. So altogether, if I multiply them, if I add them up, this is a property about chi-square distribution. Two independent chi-square sum is another chi-square. You just need to add up the degrees of freedom. So this tells me n plus m-2. Does it make sense? Right, so we are here. Then finally, right, so then you can see we have combined with the fact that xn bar minus ym bar over this sigma x squared over m plus, okay, sorry. Now we have the same sigma. So sigma x squared over m over sigma x squared over m, right? We had this under the null follows standard normal. We previously derived this. And now we have sigma x squared equals to sigma y squared. So with this, then this becomes xn bar minus ym bar. So we can combine the sigma, right? So we just have it out. We can have it equal to just sigma square. Okay, so let me see how sigma, and put it out of square root over 1 over m plus 1 over m. Okay, okay, so this is what we have. This under null follows standard normal. Okay, but the sigma is unknown. That's what we know. So we're going to rely on the T distribution construction, the definition of T distribution. So based on the definition of T distribution, we have combining these two results. So this is, let me call 1, this is, let me call 2. So 1 plus 2 would give me, I put a standard normal on top. I put a standard normal on top, and I put the chi-square divided by its degree of freedom on the bottom. So the chi-square is this, n-1 sx squared plus n-1 sy squared over sigma squared. This follows chi-square, and I will divide it by its degrees of freedom, m plus m-2. Okay, so now you can see a magical thing. This sigma square right here and the sigma right here, they can be canceled. Oh, my bad. I forgot to put a square root here. That's the key. Okay, so then we know this follows what? This would follow, and also under the null hypothesis, this follows T distribution with degrees of freedom n plus m-2. So I'm combining the knowledge we learned before to reach here. Are we all good? Okay, so last step, just some simple algebra simplification. I can tell you that sigma squared would be done, okay? And we are going to have, let me just do it. xn bar minus yn bar, I left it on the top. And for the rest, I'm going to have n plus m minus 2, n minus 1 as x squared plus n minus 1 as y squared. This thing divided by 1 over m plus 1 over m. Okay. So finally, you can recognize that this term is just my pooled sample variance definition. So in other words, I would have this as just the pooled sample variance as p squared times 1 over m plus 1 over m. Over here, I have, okay, and I can tell you this under the null follows this t distribution. Okay, and this term is what we call the two sample t statistic, but I'm still using the general notation t to be consistent. But this gets a name. It's called the two sample t statistic. Okay. So we can use it to compare two conditions, even though we don't know their respective variances. We are just adding this common variance assumption, sigma x squared equals sigma y squared. By adding this additional assumption, we can derive this statistic, and it follows exactly the t distribution under the null. Okay, and this derivation, you can see it uses all the knowledge we had before, including one more knowledge I forgot to mention is we need independence actually. So in order to say this follows a t distribution, you will need independence that xn bar is independent of Sn squared, yn bar is independent xx squared and sy squared. So you need those two things so that because there's independence requirement between the numerator and denominator for the t distribution definition. Okay, and I can tell you why that additional assumption is necessary. The reason is that if you don't have the same variance, then you cannot combine these two terms. So sigma x squared will be here, sigma y squared will be here. So you cannot just combine them into one thing. So that's why if you want to leave out this assumption by assuming they can be different, we cannot use this two sample t test. We get another test called the Welch's two sample test. So that you can Google this by Wikipedia, but in that case, we cannot use this as the exact null distribution. We can have to do some more complicated calculation in the Welch's paper as he did. So that's why that test got a different name. But I think for this class, we can stop here by understanding, yeah, this is what we call the two sample t test, two sample t statistic. Okay, so any other questions about this part? So we can use a similar idea to compare two proportions, like we have a sample Bernoulli with P1 parameter, another sample from Bernoulli P2 parameter. We can compare whether P1 is equal to P2. So we can do a two sample comparison in a very similar way. And in that case, we're going to use the central limit theorem. Okay, so finally, I'm going to give you one maybe brief introduction about a very important result in mathematical statistics, but I understand that we are just running out of time. So this last part will not be in the final exam, but I'm going to introduce it to you for your information. This is called the Neyman-Pearson lemma. So you can think of this Neyman-Pearson lemma as important as the likelihood theory, the maximum likelihood estimation theory, which tells us that asymptotically, when n is large, our MLE has a normal distribution with mean as the true parameter and the variance as the inverse of the Fisher information times the sample size, if you recall. That's the major result we talk about for the MLE. the nice property about the MLE as an estimator. The Neyman-Pearson lemma tells us another nice property about the likelihood, which can give us the most powerful test statistic. So in the Neyman-Pearson lemma, you have this simple alternative hypothesis. So let's say that we tell you theta under the null takes a value theta 0 versus the alternative theta takes a value theta 1. And we know that these two values are different. So the decision is about choosing whether you want to go to the alternative or stay with the null. Okay, so what it says is that if you have a sample of IID sample, IID from a distribution with density function denoted by the parameter theta. So the parameter specifies the density. So therefore, you can write down the likelihood for each parameter, right? So the likelihood for parameter theta 0 value under the null is basically the product of the density function at theta 0. You evaluate density at each of your random variables. This is what we call the likelihood under the null. And the likelihood under the alternative is denoted by L theta 1. And we're going to now evaluate the density using the alternative parameter at each random variable in our sample. So therefore, we can tell you that the most powerful test statistic takes this form. You just do the ratio of the two likelihoods, because you know that each likelihood involves your random sample x1 to xn. So therefore, given theta 1 and theta 0, this L theta 1 is random, and its randomness comes from x1 to xn. And also L theta 0 is random, right? Both are functions of x1 to xn. So their ratio is also a random variable depending on x1 to xn. So we told you this is the most powerful test statistic, and that's the result of this lemma. So based on this test statistic, your rejection region is that it's larger than a threshold. The rejection region is larger than a threshold. Okay, let me just call that A, where A is a threshold determined by the significance level alpha. So using the alpha, using the null distribution of this likelihood ratio, you're going to find A. So it's going to be determined by the significance level alpha and the null distribution, the distribution of this L theta 1 over L theta 0 under the null. So this result is very important because it gives you a way to construct a test, in general. So if you know the distribution, if you can write down the likelihood, then this will give you the most desirable statistic you are looking for. So the message I want to say here is that there can be multiple ways to construct test statistics, and they can all satisfy the significance level, because for each test statistic, as long as you can derive its distribution under the null, then given a significance level, you can find the rejection region correspondingly and your test is done. Or you can just use the distribution and the realization to get a p-value and compare to alpha. So there are multiple ways to do it, but they may have different powers. even though they have the same control for the type 1 error under the significance level alpha, but they may have different powers. But this Neyman-Pearson lemma tells you the most powerful test you can achieve. So that's why it's very important. So it tells you how important the likelihood role, what the crucial role played by likelihood in mathematical statistics. So basically, if you check the combined lecture notes I posted to Cecily, there is one example on the last page about how this likelihood ratio can tell us a test statistic. And you can check that out. It's about testing the actually exponential distribution parameter. But as I said, this is optional, and I'm not going to include it in the final exam because we run out of time for talking about this in detail. But I still think this is something good to mention for the end of our lectures. So on the in the next lecture on Wednesday, I'm going to do a review. So I will try to focus on the contents that we will focus on in the final and try to do some practice problems together with you guys. So then, and also please be prepared for any questions you have before Wednesday. So that will be a good place to ask questions and also listen to others' questions. All right, so, and I will see you on Wednesday. Yeah, so please be assured, I think people will definitely do better in the final exam, given that we have more time and also the format is in person and also the style is more similar to the homework. Okay. And also for the style, we're going to, for the final, we are going to give you points for the steps. So therefore, try to be specific, try to be detailed in your solution, because even if you may miss the final answer by a calculation error, but at least you can get a points for the steps. So we can see the logic. Okay, so I'll see you on Wednesday.
Thank you.
Yeah, bye-bye.